As promised, we're going to look at pendulums now. And pendulums, in case you're not quite sure, you basically take the simplest form of a pendulum, and I guess I should write this here. We're talking simple or ideal pendulums. And the ideal pendulum is a special case of a pendulum. You basically just take a massless spring, or string, I should say. So a massless string, and you attach a tiny sized mass to the end of it. And what I mean by tiny size is not taking up much space. So if you just were to take one of our normal strings and attach, a hooked mass to it or something like that, or a ball bearing, anything like that, that would be pretty close to an ideal pendulum. A non-ideal pendulum would be more like a meter stick with a mass attached to the end. You can't just ignore the meter stick's mass. It's significant. But if you look at most of the pendulums that you see, that you notice as being pendulums around you, then we can treat those as ideal pendulums. So if you're looking at a grandfather clock or something like that, there's a very thin, lightweight rod with a mass attached to the end of it. It's pretty close to an ideal pendulum. This is a very different motion in a lot of ways to the spring motion. One of the nice things about the spring is that it only goes back and forth. It stays in one direction, so it goes this way and it goes that way. A pendulum travels through these arcs, and that makes it a little bit more complicated. It's actually rotating about a pivot point, and this is really what we did in our last unit. We dealt with rotational motion. So I'm not going to really waste too much time here. Let me just pick a color that'll show up. So there's a force of gravity downwards acting on the pendulum bob. That's the mass at the end of the string. And there's a force of tension acting up on it. And we need to figure out what's going to go on here, what's going to contribute to the motion of the object. And one of the things that we should realize from our last unit is that if you have a force that's acting along the radius, then it's not going to change the motion of the object. Or I should say more specifically, it's not going to change the speed of the object. This contributes to the centripetal force, but it's not going to contribute to any speeding up or slowing down. So if we take this pendulum bob and just move it off to the side and let it go, the force that's actually leading to it speeding up is going to be the force of gravity. So I'm just going to draw that a little bit bigger off to the side here, where this is going to be the angle theta. Okay, so that's our angle theta. So the angle that we pulled over to is the same as the angle for this. And if I make it so that angular displacements this way are positive and angular displacements that way are negative, then our initial angular displacement is going to be a positive number, but the initial force will be negative mg sine of the angle, because it's going in opposition to that. And what we're going to do is, because this is rotational motion, we're not going to do a sum of forces, we're going to do a sum of torques. So we'll do sum of torque equals I times alpha. And there's only one force providing a torque in this case, so we're just going to do R. In this case, our R is the length of the pendulum, so I'll do L times the force, mg sine of the angle, equals the moment of inertia. And once again, because we just have this point mass at the end, and we're ignoring the mass of the string itself, all of this mass here is located a distance L away. So the moment of inertia is pretty easy to calculate. It's ml squared. And we'll just leave this as alpha. So what we can do then is just, if we want to, we can cancel out these L's. And we can also cancel out the M's, or at least some of the L's. So I'm going to go ahead and do that for now. I'll probably bring them back in at some point to make a point. But we can cancel those out, and then we get the opposite of g sine theta equals L times alpha. This term right here is very vexing. What it means is that the sign of the angle is what's important. But most of the time when we're dealing with pendulums, we're only dealing with relatively small angles. So if you take a pendulum and you hold it off to the side like this, we actually don't rely upon that as a pendulum type of a device. It's a little bit more complicated than that. You can get some slack in the line if it's a string, and it doesn't necessarily behave as nicely as we would like. So in most practical applications, what you'll notice is that the pendulum actually only swings through a fairly small angle. Even if you go to the Ben Franklin Museum, you have a pendulum, the Foucault pendulum, that swings back and forth, and it swings a decent distance, but it's a multi-story string that it's attached to. Maybe not a string, but it's a multi-story rod that it's attached to. And so what that means is that even though it's swinging through a fairly sizable linear distance, a couple feet, the angular displacement is very, very small. So when we talk about our ideal pendulums, we're talking about angles that are small. And what do I mean by small? Small. By small, I mean thetas that are less than or equal to about 20 degrees. You can maybe go up to 30 degrees, but under 20, 25 is pretty good. And what we do is we do something called the small angle approximation. And the small angle approximation looks like this. I just canceled out the sign part. This is very disturbing for some people. What I want you to do is take a moment and plug into your calculator the sine of some angle in radians, a small angle. So try plugging in, maybe treat theta as 0.01. And what I want you to do is take the sine of that. And what you should get out is basically 0.01. So for small angles, theta is approximately equal to the sine of theta. So we just get rid of this nasty sign and we leave it as theta. So that leaves us with this equation. The opposite of g over L, theta as a function of time, because obviously the angle changes with time, equals alpha as a function of time. And what I want to do is just draw your attention to the fact that we had something that looked like this for springs. Theta is the rotational equivalent for x. Alpha is the rotational equivalent for a. We have that negative sign, which is one of the characteristics of simple harmonic motion. It means that we have a force that is constantly trying to redirect the object towards the equilibrium. So we displace it off in the positive direction, the force will be negative. We displace it off in the negative direction, the force will be positive. What we have here is just a different set of factors, because obviously we're dealing with a pendulum and not a spring. And so our omega for a pendulum would be the square root of g over L. What this is suggesting is that the longer the string is, the harder it is to change the motion. And this should make sense if you're looking at the moment of inertia as being the factor most dominated by the length, because it has that L squared term. Then this should make perfect sense, because the longer it is, the larger the moment of inertia, so the greater the resistance to changes in angular motion it has. And that means that it's not going to respond as well to a given force. It's going to be more sluggish the longer the string is. So it's going to take longer for it to go through a cycle. The factor on the top is your restorative factor. G tells us how much it's trying to get it back towards the center. If you were to do this on a more dense planet, then it would effectively cause it to oscillate more rapidly. Whereas if you did it on the moon, where g is smaller, then the period of the frequency would increase. The rate of oscillation would decrease. And so the period for the pendulum is actually going to be 2 pi times the square root of L over G. Okay, and I flipped this term around because whatever makes the frequency bigger makes the period smaller. So we now have our two equations that really govern the period for the spring and for the pendulum. And the last thing that I just want to draw your attention to is the fact that in both cases we really had the period was equal to 2 pi times the square root of what I will call the restorative factor divided by the inertial factor. Whoops, I did that reversed. Because we really want, I apologize, I was trying to make it so that, I was looking at omega there. I could have just deleted the restorative part and the inertial part. That would have been too easy. So we have the inertial part, inertial factor, divided by the restorative factor. So these are the two major things in each case. One thing that you'll notice that's absent from the period for a pendulum is the mass. The mass doesn't matter. And you might think, well, that has to do with the inertial factor, right? Absolutely. But it has equally to do with the restorative factor, because the larger the mass, the harder gravity will try to pull it back towards the center. But the larger the mass, the harder it is to actually change the motion. So the mass ends up canceling out. And that's why we get this L over G. So one of the common misconceptions is that the mass matters for the period of a pendulum. It really doesn't. All that matters is how long is the string and what is the value for G.